Welcome to the session. Greeting of the day. In today's class, we are going to talk about a laser beam welding process. In the classifications of welding, we have divided the various processes with respect to the heat source, how the heat source is generated. We have done the heat source with respect to gases and with respect to electric arc, with respect to resistance heating, with respect to mechanical energy conversion such as frictions and explosives, and also the chemical reactions process, and now with respect to various radiant energy process, and previously we have seen about electron beam welding, and now we are going to see about this laser beam welding processes. This laser, we know already that the light amplification by stimulated emission of radiation, we know this as a lasers. At the surfaces, regarding the welding process, at the surfaces the concentration of a light energy converted into a thermal energy. This light energy we are converting into the thermal energy as a heat source to do the joining of the two specimens. The heat causes the surface of the material to heating, and then by melting, or otherwise if it is the intensity of heat is very high, it may vaporize also. Therefore, we are using that for the joining purpose. In the manufacturing, we are using the machining and weldings, cutting surfaces, modification, additive manufacturing, heat treatments. For normal heat treatments, how far the intensity of heat? If it is low, we can heat it. If it is very high, we can cut. If it is moderate, we can go for welding, melting, those things. So such as the measurements, medical applications, there are various applications out there. Specific recent days, it is finding the more advantages than that of the other welding processes. The laser falls in the range of visible and then the near infrared zones, and also it covers the far infrared zones. So somehow it is hazardous also. You should be taken care to protect ourselves from the laser falling on us. So it is a fusion welding method. Now we came to the laser, we know. Now the laser beam we are passing over the specimen, by it may be vaporized or melted to cause the welding process. Therefore I am calling it as not a solid state joining. I am calling this as a fusion welding. Melting happens there. So it is a fusion welding method in which the collisions is produced by heating the workpieces due to impinging of the concentrated beam. Which beam? The laser beam of stimulated electrons coming from the laser sources. It is a device that produces a concentrated coherent of light beam, a single frequency by stimulated electrons or molecules transitions to the lower energy levels. So in a laser beam welding, we should understand how these lasers are generated. In laser beam welding, the laser beam is directed by a flat optical elements such as mirrors and then focused to a small spot or high power density at the workpieces using either the reflective method or otherwise the lenses method. Before going there, we should simple some understanding ought to be there to us. See, there is the atom which contains ions and electrons. We know this, and it is contain orbits. Various orbits are there. So from inner orbit to the outer orbit, orbits are there. In these orbits, at center, neutrons and protons are there. At outer valence cells, before inner cell, outer cells, we have the electrons are there. So these electrons are here. We have electrons here. We have electrons there. When it exhibits more energy level, these electrons are getting unstable. When it is getting the energy, at few energy it will absorb first. The atom will absorb a few energy until it accepts. If after that what happens? It started to reflect outside. So it become unstable. Therefore, when these unstable electrons will be reflect and try to jump over to the another shell, outermost shell, from the outermost shell to the another shell to get stable. So I am telling this inner shell contains the energy E, it is E1, and the next one having the higher energy, that is E2 greater than that of E1, and the outermost shell will contain E3 greater than that of E2. There is a difference. There is a difference of del E is there. So therefore del E equal to E3 minus E2. So this difference of unstable will causes these electrons to exhibit the photons outside in terms of a monochromatic rays, which is called as laser. In terms of laser, it exhibits to come out to become stable. These lasers we are going to use there. So this difference causes unstable. When the inside energy is given, this started absorbing, and after acceptance maximum level, it started to release. That is, release is unstable, which is ready to go to become stable. That electron releasing in terms of laser that we are going to use and take. So that is what a simple understanding for us. So from there you see, so here I want to give energy to exhibit. How I am doing? I am using the laser pump or power supply of a laser pump I am using. See, that is a lamp or diode I am using there, which I am passing the light source over the atom or over the laser material. We have studied that the ruby crystal, it is one of the laser material. In the physics we have studied those things. Such in that we are passing a lamp, it means energy we are passing inside through to this ruby crystal. What happens? These unstable energies will come out and exhibits in terms of laser forms. So that it's to be multiplied. How we are multiplying? I am keeping one end of the crystal. You see, the positives, ions and electrons are exhibiting here and there in this laser active medium. This is the laser active medium, and this is the laser pump from where we are supplying the lamp, in which it started to exhibit and getting unstable. We are making it unstable. That the electrons are bombarding themselves inside and multiplying themselves, because unstables are wanted to become stable, but we are keep on supplying the lamp light. We keep on energizing the ruby crystal, or otherwise the laser active medium. We are keep on energizing. If we keep on energizing, it's keep on unstable. If it is keep on unstable, we have at the left side one mirror which is completely 100% reflective. It is completely 100% reflective. And at the other end, we have a moderate through which the laser beam can pass through. So see, it is one as a mirror and then a focus on a small spot. This is a small spot where the another side they have mirror through which it can pass through. So one side 100% is reflective, it is partially reflective. The other side mirror 2 is partially reflective. So what happens during this bombardment takes place, even though it is multiplying, the energy, high intensified energy density is formed there. As like in electron beam welding, here also 109 kilowatt per centimeter square possible to make. This are passed out through a partially transforming zones. There we have the workpiece. At that end we have workpiece. Therefore it is paused. Always it is coming at high energy with high heat. This heat has to be fall on this specimen to create the welding process. So for this laser medium, maybe the ruby, maybe the CO2, maybe the NDR combination solid state lasers. Some methods are there that we are using as a laser medium. So see, here I am saying from the top view, here I have this laser, we have to energize. How to energize the lamp which contains a krypton or xenon flash lamp focusing optics. So see, this contains a krypton or xenon flash lamp which is falling over the specimen. We have the lamp box, the laser medium. This is the laser medium. We have the laser medium here. We have the laser medium here, and this with respect to flash lamp I am supplying. With respect to flash lamp I am supplying here. I am supplying here. So similarly here also. The radiations are passed to energize the rod. This energizes the ruby rod or maybe the laser medium. Therefore, from there, from the medium, it is getting reflected. It is getting. See here, these all electrons are formed, and then it is getting reflected here in the 100% reflective mirror, and then it is coming back. It is energizing. It is coming back, reflecting, and there in this side we have a partially reflective mirror. Here and there, to and fro, the bombardment takes place and keep on energy also given through the xenon krypton flash lamps. This makes the multiplications of the energy density. It means it is heat we have generated. That heat, laser converted to heat, that heat we are going to use for welding process. Now we are through this partially reflective, the material comes out. Material comes out and it is falling on the specimen. Maybe for welding, maybe for cutting, maybe for heat treatment. That is, the laser beam is generated with a high intensified heat. That heat can be high heat, we can use it for cutting and weldings. Low heat, we can use it for heat treatment processes. So that is what, see, if an atom is already at high energy, absorbs the energy now, through which one? Through this xenon or xenon flash lamp, we are absorbing energy. It will emit the remaining all the absorbed energies. This amplified light beam is called as laser. First it absorbs, later it emits, it is amplified way, multiplied way it is releasing. That is we are naming as a laser. The laser material may be ruby, absorbs energy to some extent, and later what is did? We are supplying here the energy, it's absorbed. Then what it is did? The release is when it reaches its absorption limit. So this we are converting as a laser and we are utilizing for heat and welding purposes. Power supply. What are the components now we have? We need to power supply. It provides energy for excitation of electrons from the low energy level to the high energy level. That flash lamp. Laser discharge tube where the ruby crystal is kept inside, or maybe the other India solid state lasers are kept inside the box, the laser medium. Laser material is filled inside, so maybe ruby. And then it is, one side is partially transparent, one side, that it means the welding side, and the other side is 100% reflective. What is the laser material or what we are using? Maybe the CO2 which emits light infrared region, because this CO2, see, CO2, ruby, NDRs all comes under these zones. So this laser zone it is coming there. See, it is all comes under here. See, the NDRs and CO2 all comes here, and ruby also. See, all comes in this laser zones. So that we are using. This and multiplies. That source we are using. It emits laser sources when it is energized first. Right? So solid state lasers. These are not solid state lasers which we are using. Working. The gases get filled in that laser discharge tube. It means we are talking maybe the ruby or CO2, whatever, the gas laser or solid state ruby lasers. When lamps produces the light energy, when the flash lamps produces the light energy which excites the electron of an atom, taking out energies. This leads to jump of electron from low energy level to the high energy level. It means from E2 to E3. So the atoms become unstable. So the atoms become unstable at a high energy level. This energy initially blended up in a laser material to multiply the emitted energy. These laser lights are collected by a focus lens and directed to the workpieces. For which one? For welding. For welding, cutting, heat treatments, whatever it is. So they have given. Here also it's there. They have given. Right? See? Now we came. See how far the thin materials they are welding. We can able to do, though it is intensified, keeping arc length, the lasers can be operated at a long distance also, short distance also. Okay, short distance laser, long distance laser. So here, as like we have seen the electron beam welding, intensified heat, keyhole welding method, here also we can able to make a keyhole welding process. Here also we are making the keyhole welding. See, here also we are making the keyhole welding process, a narrow heat affected zone, because the required focused heat we are supplying for the flat specimens. We have taken 2 specimens, no edge preparations. Here also we no need of doing that, such an edge preparation not there, and we are supplying the intensified heat here. It puts a keyhole. And it is after putting keyhole, the material at the failing surfaces are again act as a rectifiers, and then it can able to fill the gap, and the welding is occurred. You see, here I have given electron beam welding. It have high penetration here. Laser beam welding, it also having the high penetration there. So other process, GTW very broad only. SMAW very broad and also having little bit penetration, but not equal to laser beam welding, electron beam welding. It is somehow shorter only. GMAW and SAW having full penetration. But what is the problem there? We have high, width also is high. If width is high, here this zones belong to heat affected zone. This zone belongs to heat affected zone. That is not good. So heat affected zones are brittle, bottom side, not recommended. So we are preferring electron beam welding and laser beam weldings. So see, this is the keyhole. It is a non-contact process. Yes, we are not going to touch through the laser. It is going to vaporize or heat, requiring no pressure to be developed. Pressure not applied, no contact method, only heating, direct laser heating. Inert gas shielding is generally employed to prevent the oxidation of the molten puddle to filler material may become occupied. Therefore, I am telling energy transfer mechanism is different from the arc welding process. So in the arc welding process, what is the energy mechanism? Electrical energy converted into heat energy. But here the same electrons are converted. This bombardment of electron flow is converted into heat energy. So that is different, entirely different radiations. The radiations are converted here. Absorptions of energy, laser matter interactions. The laser output, not electrical in nature. See, the laser output is not, the arc is electrical output. When your conducting material is conducted, thermal conductivity is there, absorption is there, some other things happen. Due to electrical conductivity, magnetic fields also will be generated, but nothing is there. Laser output is not electrical, it is a heat. We are going to use for the welding process. Non-electrical in nature, eliminates any effect of magnetism. Not required a flow of electrical current, no need of electrical current. Just a flash lamp is released. X-non flash lamp is released with the energy, electrons energy. Not limited to the electrically conductive material. Does not require a vacuum. This we have vacuum in this electron beam welding, but here not required. It does not produce X-rays. But in electron beam welding, due to this emission of electron, X-rays also generated. But here no X-rays, no vacuum. It can able to operate at room temperature. It can able to operate at any locations. Any free environment we can able to operate this laser. So the advantage limitations, you see, therefore I am telling heat input is very close to the minimum required fusion only. specific point, the flash lamp generated, heat generated, we are focusing at the specific point and it is vaporizing and putting keyhole and it is depositing the spraying surfaces, dropping down and melting, and welding is done. There is no chance of extra heat is given to absorbed by the remaining zones. There is no heat affected zones there, only specific location, point heating occurs there. Therefore, so narrow or nil heat affected zones. So these are all advantages of the laser welding treatment. I am telling here that therefore no electrode, no flux, no vacuum. Now only we have told at any temperature, any working environment, take a room temperature, we can able to operate. No vacuum, no X-rays. Same point. Non-contact process, yes. No magnetic field, as there is no electrical supply, no conductings, no magnetic fields are generated. All position welding, like 6G positions or 4G positions, any positions we can able to weld, we can able to operate nook and corners. The laser is going to there and they are going to go. We don't need to go there. We can operate from here to there. The intensified beam has to be centered there. All position, good access. Therefore, it is good accessibility. Laser passing. It is easy to pass the laser only. So therefore, good accessibility at critical situations or difficult situations also. Tiny welds can do, a small area can do, a thick area also can able to do. So from tiny to thick. That is what dissimilar welding. Any material, dissimilar materials we can able to join because intensified heat the specific point. It does not melt the remaining part. Aluminum also possible to weld there. Aspect ratio is 10 to 1. It means the 10 is with depth and this 1 is width. So this width. So we can able to show the keyhole welding process. Small intensified heat is supplied here. Intensified heat is supplied here and we are going deep on doing the penetration. The thickness we should need. We no need of this heat affected zones. This heat affected zones we no need. This heat affected zones we no need. Therefore, depth to width aspect ratio is very good. Automatic high repeatability. As it is automatic process, in setting the parameter intensified heat, this much heat density to be applied. Then applying the same parameters, same results we can obtain. Automatic, good high repeatability therefore. What's the limitations then? Accurate alignment to the beam. The beam is there, accurate alignment to be there. Whether maybe we have to move the workpiece or if it is compact, otherwise we have to move the position of the laser beam. So accurate is needed. Weld penetration is greater than 19 mm, somehow it is difficult. Laser beam greater than 19 mm, by the technical they are telling it is 19 mm greater than difficult to travel of this laser beam. High reflective and high thermal conductive materials are like aluminiums or copper to difficult welding because aluminium is a reflective material. Good thermal conductive material, it absorbs more heat. It reflects the laser beam. Therefore, somehow it is difficult to weld their aluminum and coppers. So, finally lasers are harmful also. What is the applications there? As it is having a numerous, no heat affected zone, there is no break. Between is not there, good ductility. Therefore, we can use in defense, aerospace, automobiles, aerospace we are using. Marines, medicals, building constructions, electronics, everywhere we are using there. Power generations, alternative energy devices such as fuel cells, solar powers, wind turbines, in the nuclears, oil and gas industries. See? Oil and gas industries, the power, pressure vessels, boiler plants also we can able to do. Home applications, regular uses, we can able to do. In the electronics, mobile parts we are doing this, laser welding we are doing. Minute micro points. There are two methods are there. In laser beam optics, short focal length, long focal length. The faster weld speed, heat losses input. See, short focal length means we are keeping contact very nearby. Long focal length, we are keeping the long focal length there. What happens if the long focal length is there? It will be distributed to laser is distributed everywhere. The point is kept like a torchlight. When the torchlight is going nearer to the wall, it focusing is very corner. When the torchlight is away from the wall, the light spreads over there. The same method. Short focal length, minimum point. Long focal length, high heat is applied to the everywhere. So therefore, if it is spreading, similarly weld spatters will form. It should not be spreaded, it is to be pointed. That is the idea here. So I am telling it may be the conduction mode or may be the keyhole mode. For the conduction mode, the power density is less than 106 watt per centimeter square. For the keyhole method, it is exceeding the 106 watt per centimeter square. So see, heating the workpiece above the melting temperature without vaporizing. Here in the conduction mode, we are making the heat to melt only, not to vaporize. Therefore, it's melted and these locations are welded. But here the molten metal starts to vaporize. It means the zone where the intensified heat is applied, the zones are vaporized. This material is not there. This laser beam length, the beam width, it vaporizes the material. Material won't be there. What happens then? The surface materials which having during this beam passing, that point will be vaporized. The adjacent points will be molten material. Those material will fall there and it will fill the gap. So that is the point. Opens up a blind hole. Therefore, this vaporizing opens up the blind hole, that is we are calling as a keyhole in the molten material. Therefore, vaporized pressure from the hot material keeps the hole open during the welding, increases the energy efficiently and welding due to multiplication of high cavities. So we can able to do more deeper penetrations also in the keyhole made. So in the penetration is controlled by the conductions only in the conduction mode. So it means conduction mode, melting and less thickness, less depth welding has been done. Less thickness and less depth has been done. But in the keyhole welding, deeper penetrations are done with respect to high power density of greater than 106 watt per centimeter square. So this is how it is. See, conduction mode, low welding depth. So what I told, it comes here. The low welding depth is less. Here welding depth is less here. But here they have a large welding depth. Small aspect ratio, low coupling efficiency, very smooth, high aesthetic weld bead. But keyhole welding is not like that. High welding depth, your welding depth is high. Similarly, width also is reduced. Width also, here is large width, but here is the small width. High aspect ratio nothing but this is 10. This is 10, this is 1. But here, this become 10 and this become 1 or 2 or 3. The aspect ratio is different. This is less aspect ratio, high aspect ratio. So high aspect ratio, see this high aspect ratio, where here we have very small aspect ratio. High coupling efficiencies. So that is how I want to compare now this both electron beam welding and laser beam welding. As we have seen, the both are radiant energy process. Weld zone and heat affected zones. Both in cases of it is very smaller in the electron beam focused. Here also it is focused. Penetration. It having a deeper penetration, but there greater than 19 mm somewhat it is not possible. So therefore it is a lack of small penetration compared to this. But there also we are going for the deeper up to 19 in a single stitch. Welding speed very high. Here it is high. Shielding gas, it is not required. Here if required, because this is done the vacuum, therefore shielding gas not required. Here we are doing the room temperature, therefore it may be required. We can give the argon shielding. No reaction to be takes place, therefore inert shielding we are giving. Vacuum chamber is required. Vacuum chamber is required here. That is not required. We can do in atmospheric. Cost, it is very high. Comparatively low, but it is also high. Laser as compared to SMIW, it is very high. Generation of X-ray, yes, it is there. X-ray will be possible. It is no. Power efficiency, here also 80 to 90% of power efficiency is there, but here 10 to 20 only. Size of workpieces are limited due to very limited due to the vacuum chamber, the box, vacuum room. So therefore size very less. But here the machine can run throughout. We have a roller setups. Therefore not limited. So it is this a simple comparison. So I want to do now this laser hybrid process. Through laser what we are getting? Through laser I am getting the laser intensified heat. This intensified I am using for welding, but I want to avoid the heat affected zones. More heat not applied from the total high arc length. I am using the hybrid method. The hybrid welding involves use of laser in the combination with the Second energy source such as arc welding process. Maybe arc welding, big TIG welding, or otherwise maybe the MIG-MAG welding process we can use, because we are using the laser treatment. We are using the laser treatment to specific point to heat there, and it is heated. After heating, we can melt the filler wire here and we can deposit hybrid. We need a keyhole intensified depth of penetration high. Therefore, I am using the laser there to point out, to make and penetrate. Vaporized, hole is created. Then I am filling those things with the hybrid arc fillers. So you can add filler here and we can able to weld. So some other hybrid methods they are doing. So what I am doing here, heat source of hybrid, primary heat sources, laser. And we have laser, CO2 laser, fiber lasers I am using. What is the second source of heat? Primary heat for making the keyhole. So it is a keyhole. These holes to be welded through the second heat source of arc welding method. So such cases we can able to do. At overall, this hybrid efficiency is greater than 80. You see, there we have studied TIG welding arc efficiency is 60%. When I am combining with the laser, it is getting that 80% of thermal efficiency we are getting. Ability to bridge the related large gaps easily, and slow cooling rates we can able to do. Slow cooling due to lower welding speeds or heat inputs can be avoided. So these things are possible. So welding a highly refractive material is generally not difficult. So metallurgical welding can be adjusted and large gaps can be filled by the adding of the filler material. So the summary. In welding, in today's class we have seen about the radiant energy process. In that we have seen about the laser welding and its working and its applications. The remaining part of the subjects see you in the next session. Thank you.